Hi, in this video, we will still learn about boundary work, but focus on a polytropic process. During actual expansion and compression processes of gases, pressure and volume are often related by PV to the power N equals C, where N and C are constants. A process of this kind is called a polytropic process. A general expression for the work done during a polytropic process can be expressed in pressure terminology. Pressure equals a product of a constant C and total volume to the power of negative N. Substituting the pressure relation for the polytropic process into the boundary work equation yields a given expression. For an ideal gas, the boundary work equation can also be expressed in the given form since PV equals mRT. However, for a particular case of N equals 1, the boundary work becomes the given equation. For an ideal gas, this result is equivalent to the isothermal process. Example 4.4 demonstrates a gas in a piston cylinder device equipped with a linear spring that expands due to heating. The final gas pressure, the total work done, and the fraction of the work done to compress the spring will be determined. Before we solve the problem, we must first specify reasonable assumptions to simplify our analysis. Three systematic steps can be used to determine the absolute final gas pressure, the total work done, and the fraction of the work done to compress the spring. First, we must determine all the related states of air using the given information. Second, we sketch the process curve on a PV diagram. And last but not least, establish the equations to be used to determine all the above. For state 1, the gas initial volume and pressure have been given as 0.05 cubic meters and 200 kilopascals, respectively. For state 2, we can quickly calculate its total volume since the value doubles the initial volume due to heat transfer to the gas, causing the piston to rise and compress the spring. Therefore, the total volume at state 2 is 0.1 cubic meters. The gas pressure at state 2 can be determined by summing up the additional pressure due to force applied by the linear spring at the final state and the initial gas pressure. The additional pressure denotes delta P subscript spring equals a ratio of the force applied on the gas by linear spring and the piston cross-sectional area, A subscript piston, where K is the linear spring and delta X is the displacement of the piston. Delta X is a ratio between the total volume change between the final and initial states and the piston cross-sectional area. Therefore, it comes to be 0.2 meters. Thus, the force applied by the linear spring comes to be 30 kilonewtons. Once we know the force, we can calculate the delta P spring and eventually the absolute final pressure of the gas is 320 kilonewton per square meters. After the relevant properties are determined, we can sketch the process on a PV diagram. Without the spring, the pressure of the gas will remain constant at 200 kilopascals. However, the spring reaction has increased the gas pressure linearly from 200 kilopascals to 320 kilopascals. The gas pressure at the final state is simply 320 kilopascals. The total work done is equivalent to the area under the process curve plotted on a PV diagram. The area under the process curve is a trapezoid, as described in the illustration. Thus, the total work done comes to be 13 kilojoules. The work done against the spring is determined by calculating the triangular area, and it comes to be 3 kilojoules.